My name is Michael Glinski. I am a professor at the Faculty of Medicine of the Technical University of Dresden in Germany. And I am heading the Center for Translational Bone, Joint and Soft Tissue Research. And we are utilizing the bioscaffolders of company GeSiM now since over 10 years. One example of many studies we have done with these printers, you can see here. This is a printed model of a part of the human knee joint. Specifically, this is the lower part of the femur bone, meaning that's located in the knee joint, but the lower part of the femoral bone. And in this joint, quite commonly, defects of the articular cartilage can appear. And in many cases, those also affect the underlying bone tissue. So we have quite deep defects consisting of a layer of articular cartilage, but also of a layer of the underlying bone tissue. And to treat those, it would be very beneficial to have implants, which on the one hand side consists of two different materials, mimicking both the non-mineralized articular cartilage and the mineralized underlying so-called osteochondral bone tissue. But of course, they also need to perfectly fit into the defect concerning size and dimensions. So what we have done here, what you can see here, is an printed plastic model of this part of the knee joint, femoral bone. You can see here the defect site, and this underlying 3D data set was taken from a patient from our university hospital from an MRI scan. And so we have a clear information about the thickness of the chondral layer as well as of the bony layer. And with the help of the GeSiM bioscaffolder, we then have printed on the one hand side perfectly fitting concerning size and shape, perfectly fitting concerning the thickness of cartilage and bone, bilayered implant, and the bony part is consisting of a self-setting calcium phosphate bone cement, whereas the chondral part is consisting of a biopolymer-based hydrogel, and that of course also can be combined with live cells. So this is a bio-ink, and as you can see, this implant now perfectly fits into the defect, and especially the superficial surface is really smooth, meaning that the implant reconstructs perfectly the shape of the chondral layer of the knee joint. Additive manufacturing in principle offers the opportunity to produce patient-specific devices, implants, which is already used also for conventional, non-degradable types of implants. And such patient-specific devices logically better fit to the specific anatomy of the patient, and therefore in many cases support a faster and a better healing. In this specific example, we are providing a degradable material combination. We are not aiming in replacing permanently a part of human tissue, but we are supporting the self-healing process so that over time both the bony part of the defect and the chondral part of the defect really can completely heal by forming again natural biological tissues. So patient-specific implants already are used in the clinic. That is a quite complicated process because regulation of such patient-specific devices is not so easy. In this specific example, we are combining one clinically approved material, and this is the self-setting calcium phosphate bone cement. This is a material which directly can be used in the clinic for patients, but the cell-laden biopolymer ink, so the bio-ink we are using for the chondral part of the construct, this is not not approved yet for the clinic, and therefore that is still some way to go so that we would get a full approval, both of course for the materials and also for the processes, which then have to be performed completely under GMP conditions till we can really utilize it with the patient.